So, going to do another little video here on the interaction of these particles. So, how do they interact? I went back to the thicker pen here. How do the particles interact with each other? And it's basically the four forces, four fundamental forces in nature. Okay, so basically all the forces that you ever see or feel, your frictions, your gravity, your all the kind of things you think you feel, normal forces, all these things, they're all combinations of these four forces in varying amounts that make you think you're feeling these other forces, but ultimately it's just these four. And I'm going to try and list these out across the top and then kind of fill in underneath what they are. The name will be kind of like what we do here. So a name of the first force and then the second force. So the first force and the strongest force, strongest, I say that word, I kind of want to do my fingers in air quotes here, and I'll talk about why in a bit. I'm going to go through it just normal, and then I'll kind of correct some of this stuff. It's called the strong force. Good name for it. And the strong force is the strongest of the forces, and what does it act on? And it acts on quarks. Okay, so acts on quarks, so that's our strong force. And then the next one we have is the weak force. The weak force. And the weak force is the second strongest. It would be basically greater, or it's less than the strong force, but it's going to be greater than the other ones we put. And this guy acts on quarks and leptons. Okay, I didn't write that very well, but that's leptons. After the weak force, we go down a step and we have the electromagnetic force, which I'm just going to write as EM. The electromagnetic force. This one you're used to. We've studied it. It's the force that acts on charged particles, so charges. It acts on things that have an electric charge. Then we go down to our poor weakest little thing here, and it's gravity. And again, I say weakest with quotes, and this acts on anything that has mass. And it turns out that later we find out this acts on things that we wouldn't even think of as having mass, like photons, so light. So this does affect things that aren't just necessarily mass related, but as far as particle physics talking, we're just talking about this just acting on stuff with mass. So strong, weak, electromagnetic, and gravity. So what causes each of these forces? And so basically what this is thought of as a particle exchange. You could think of maybe two astronauts floating in space, and one of them, so let's say here's our astronauts here, let's draw them as stick figures. So just two people floating in space, and one of them has some heavy object here, and he throws it at the other guy. Well, what's going to happen is this guy, because of conservation momentum, if he wants to push something to the left, he's going to move to the right, and when this guy catches it, again, conservation momentum, he's going to get pushed that way. And this would explain how these forces could exchange a particle and cause things to repel. And we saw repulsion in electricity and magnetism. You could make magnets float and like charges repelled and that kind of stuff. But this kind of idea, this little model here, doesn't exactly explain how does it make things attract, right? Because this only can, if you're in outer space throwing stuff back and forth, the best you can do is, push each other apart. So how do you throw a ball or a particle or something at another person in outer space and make y'all get closer together? And the answer is not quite that simple. It's kind of a statistical probability thing from when I did it in quantum. It's basically that when there's this particle exchange, there's an uncertainty in the positioning of the thing that gets exchanged, and it's just gives you this probability that they'll come closer together. Or you could think of it as it's almost like you threw a particle that had like negative momentum to it, maybe, And so when it hit this guy, instead of pushing him the other way, it pulled him that way. So even though this particle is moving left, it had like a negative momentum in the opposite direction kind of thing. I'm really not sure. I don't know of a great way to really explain it at this level. In fact, I don't even think I know a great way to explain it even at the highest level without just saying, well, we can work it out mathematically, and we have this big probability wave that makes them be closer together. So it's not really very intuitive, but it's there, and it works out mathematically, and it really describes what we see, so it works pretty well. So it's a particle exchange, and so what particle then actually causes it? Well, for this one, it's called the gluon. And in a moment when I tell you what the strong force does, this name will be easily rememberable. Over here, we have 3 different particles that cause this. It's the W plus, the W minus, so I'm just going to write it that way, and the Z bosons. And remember, bosons, we said, were force-carrying particles. In fact, a gluon is a boson. And then for electricity and magnetism, it's simply the photon. The photon causes this guy. It's actually called a virtual photon, but the photon carries the electromagnetic charge. And then over here, we have a particle that is predicted, or according to the theory is supposed to be there, but it's never actually been detected. Nobody's ever found any evidence of this, but if they did, it would be called the graviton. And it too would then be a boson as well. But we're going to put a little question mark or something there because this guy's never been found. No one's ever detected it or found it. So it's actually a big problem with this particle physics is that this gravity just really doesn't want to fit in with the other 3 forces. It doesn't want to work well with them. And so it's kind of been a big thing. The particle physics stuff works really well for these 3 forces and explains them very well, and then it fails with gravity. And then, conversely, all our gravity theories like general relativity and stuff work really well for gravity with no particle exchange, but then they really don't work well over here. They don't predict what happens over here very well. So it's still kind of that division, and this guy's still a big kind of mystery as far as particle physics is concerned. So what does the strong force do? Well, this is the guy, excuse me, responsible for holding the nucleus together. It holds the nucleus together. You have a whole bunch of positively charged things down in the nucleus, and this guy is the strongest force. And so these positively charged forces that would want to repel due to the E and M force. So this just causes, I'm going to just go ahead and write it here, the electricity and magnetic forces. So fits its name. But this guy basically is what holds those together over that Coulomb repulsion that would be caused by this, because he's much stronger than the electricity magnetism force. This weak particle here is responsible for radioactive decay. So decay, that's what this guy causes. He causes our nuclei and other kind of things to decay. And then, of course, this one is responsible for gravity. Okay, these 2 just fit their names, and they go along with it. Now, you may be asking yourself, why is it that if the strong force is the strongest and the weak force is the second strongest, why aren't these 2 dominating the universe as we see it? Because when we look out there, mostly what we see is gravity. Gravity is the one that's still dominant. Now, we talked before about electricity and magnetism, the electromagnetic force, being stronger than the gravitational force, typically, but we explained that gravity was more dominant on the large scale of everything because electromagnetism basically canceled itself out. It had positive and negative charges, and overall it made everything pretty much neutral on a large scale, and so it kind of canceled itself out. But gravity couldn't cancel itself out, so it acted over this large scale, and it was like the dominant force we saw in the whole universe. Well, but what about these 2? These 2 don't dominate the universe, and it's not because they cancel themselves out like the electromagnetic force does. It's because they're very short-ranged. So they all have a range. How far over do they act? And this is a very short range. And I mean short, like down inside the nucleus short. And the same thing here. They're very short range forces. They don't act over a very long distance. So if you get some quarks just a little bit further apart than they are, then this strong force stops acting on them, and then you can get dominated by these other forces at that point. And these two forces are basically thought to be, they act over infinite distances. They act, forever and ever, whereas these guys are very short. So even though they're stronger and they dominate like down on the small particle scale stuff, they don't dominate the large scale stuff we see every day that we're used to as these two. This is what we see and what dominates everything. Now, I said before that this was the order of strongest to weakest. Well, you have to take that kind of with a grain of salt, because you'll see that a lot. In most physics textbooks, you'll always hear people saying that, like, electricity and magnetism is stronger than gravity. Well, I think it really depends. I think the question isn't, why is this one stronger than that one? And it's more a question of, why does an electron have so much more charge than it does mass? Because remember, we described charge as basically electric mass. And so why is it when you have a single electron, why does it have so much more of this electric mass, this charge, than it does just inertial mass, this gravitational mass? And that's really the question we should be asking. So this kind of ordering you take with a grain of salt, because if you're talking to a neutrino, a chargeless particle, it's going to see, or a photon or something, it's going to see gravity as a much stronger force than the electromagnetic force would. And if you can somehow could just increase this mass of an electron, then you could make gravity a stronger force. So it's really more, why do these things have properties that they interact with these forces in various amounts, rather than why are these different forces stronger than the other. Now, for your tests and stuff, you need to basically remember this order, that this is the order of their strength, because that's how it turns out to actually work in this universe. But deep down, think, why does so much matter have so much more charge than it does mass? Think along those kind of questions, those kind of terms, rather than why is one force stronger than the other. So going from there, this leads us to talking about confinement. Okay? So before I said we had those quarks, and the quarks had those fractional charges where they could have 2/3 or minus 1/3, or if they're anti-quarks, then they're the minus 2/3 and the plus 1/3 or everything like that. But what is this confinement thing? Why can't I then have a fractional charge? Why can't I just grab a single quark by itself and say, oh look, I got a quark with 2/3 charge, I now have less than the fundamental charge? Well, it turns out that nobody ever finds quarks alone in nature. No one ever finds quarks alone. All right? They always are at least in a pair. And the idea behind this is, it turns out that if you have two quarks, quark and another quark here, and they are bound together, that it takes the amount of energy it actually takes that you have to put in, all this energy you'd have to shove in there to break them apart. It actually turns out that that's the amount of energy that's required to create two new quarks. So if you break that quark away from this quark, what happens is two new quarks are created that are then bound to the newly separated quarks. And so even if you try to separate them, get enough energy to separate them, you just end up creating new quarks, because remember, E is mc squared, and we can turn energy into mass and vice versa. And so we'd end up creating this kind of mass just by doing that. And so that's kind of an important thing you need to remember, is that if you go excuse me, and try and create split quarks, you may split them, but you create two new ones in the process, and you still always end up with pairs of quarks and never an individual quark. All right, and the last thing for this video is the Higgs field, or the Higgs particle, the Higgs boson, sometimes I believe called the God particle. But it's essentially, there was some trouble, because as I said, some of those particles we talked about in the last video. Remember this guy here, and we had the 8 different types of particles we could have, and we had all the quarks up here, and we had all our leptons down here, and then we had all our bosons over here, right? Remember that thing? And we went along and we looked at some of these, and I said, you know, these guys here are cousins of these quarks, and these particles are all very similar, right? We had our neutrinos here, and we had our electron here, and our up, and I think, where was that one? I'm gonna have to look now. Up, down, charm, top, strange, bottom, muon, a tau particle, just to fill those out. We had all those particles there, and that's a mu. And we had these particles here, and I had talked about how they were like cousins of each other and they were related. Well, mathematically speaking, and most of property speaking, you know, these particles are not all that different. They're very closely related, but yet some of them had mass and others didn't. And the same thing with the bosons. Some of these bosons seem to have mass and some did not have any. And so it kind of made things a bit troublesome. And so we had to basically come up with this idea. Why did some of these have mass and some of these didn't? And so out of necessity, this idea was this Higgs field. It was basically this big array of particles, or this big field of particles that permeated through all space, and the amount of mass something had depended on how strongly it actually interacted with this Higgs field. You could think of it like a river. This Higgs field is, or a big giant lake that everything is in, full of water. And some particles would interact with that a lot more strongly than others, kind of like a nice streamlined jet boat would just cruise through the water, right? So, here's our Higgs field, and we have this nice jet boat, big engine on it. It's nice, it's streamlined, and it cruises through the water, and it hardly feels the water at all. But then you have something that, here's our water, you have some big square box or something in here, and you try to push it through the water, and there's a whole lot of drag. Whereas this guy can just zoom way off. This guy, on the other hand, he's just going real slow, and there's a lot of drag, kind of stuff, holding him back from going as fast as the jet boat, where the jet boat's not going to feel the water as much, and this guy feels a lot. Well, it's that same kind of idea here. Some particles feel this Higgs field a lot more than others. They interact with it a lot more. And so this idea was theorized. And then for a long time, it was thought that we wouldn't really be able to detect it until they built the Large Hadron Collider. I'm sure you have possibly heard of this thing. It's a big collider for hadrons, which we talked about. And this thing was the biggest particle accelerator in the world ever made. And so they thought if anything could actually detect this, it would be this. And sure enough, they went and they were able to basically indirectly detect this thing. And so according to the theory, this particle, the Higgs particle, responsible for this field, would actually break down and turn into 2 photons. And the photons would be at about the 125 giga electron volt range, right, for the amount of energy. And then if we counted the number of particles, the number of photons, or the number of events as they like to call it, what happened was it went down, and it was this nice smooth curve, but then there was this little bump right along that 125 gig electron, right where it would be predicted that these extra photons would be created by the decaying Higgs particle. And so this was seen as this great triumph, of this big evidence that the Higgs particle was actually there, and it was a big deal for particle physics, and made a lot of people who worked in particle physics and spent a lot of time working on this experiment very, very happy to have discovered this, or at least indirectly discovered it, by finding this little teeny tiny, and I mean small, little bump in their data right where they expected it to be for the Higgs boson. Alright, so I think that's about all I had to say for this video, and I'll see you